have pre-built locally.
But the graph structure isn't fixed, right? I mean, that can be.
Yeah, so they go and update it, and so they probably do something like a little bit. There are probably some various optimizations they do now, but I know in the mid-2000s they would rerun PageRank every night based on the updated information they got back from their crawlers. So they would rerun it every night, and they would recompute this PageRank matrix, and so then the next day it would have an updated importance.
But the crawler information would be dated.
Yeah.
Because it takes so long to run it through.
So it's the same thing. If you updated your web page, and Google hasn't recrawled it, then it won't know that you have had a whole section about pi on the web page, right? If you added it, so it wouldn't change its index at all to have that until a crawler went to it again. Same way, if you update a link, it wouldn't rechange this probability transition matrix until a crawler went back. So it's the same issue.
But you could probably update it like one site at a time, so you know like the New York Times is going to change every day, and you know this other site isn't. If you had a matrix, I assume they probably don't, but if you had one, you could just update one column, right, and just say. Like,
Yeah. So you don't need a crawler. Now they have. I think something like. I heard something, I don't know how much this is crawler, but I heard something like 30% of all web traffic is automated now. It's not actually people surfing on their own. It's actually something like a crawler or some other automated thing going and retrieving information. So Google has a ton of these things going on, and they know which web pages are changed more often, and they will send the crawlers back to those with higher frequency than a page that's been static for the last month. So they will rerun it, and if the page hasn't changed for a month, then they probably won't feel that they need to go back there for at least a month. There are various algorithms they can use to figure out how long to wait. But so the more frequently it's updated, the more frequently they'll index it. Now, New York Times, whenever there's a new story, they probably are notified of it and will try and build an index. There are very different things they do for very recent data. Up until I don't know if you remember how search engines worked, say 5 or 8 years ago. Say 8 years ago, they were very bad about recent data. You couldn't search news stories. That this was a relatively recent development. They needed to kind of have a different way where they indexed news based on the recency in a different way than they did this PageRank. So if things updated very frequently, they need to use slightly different techniques. It's still related to this, but you need to kind of give some more weight to more recent items in various ways. They're not going to have as many links yet because it was just up there. But if it's on the New York Times, probably a lot of people are reading it anyways. So you may want to kind of index that. Okay, so this is kind of the core machinery behind it. There are lots of other things that have been added on, and some of this is black magic. Some of it is internal to Google and is very scientific, but they just don't want people to know, because the more you know about the algorithm you use to rank these, the easier it is for the web pages to kind of fool that out. So they actually kind of keep some of this magic. Also, some of the reason that they don't release this is because it's not done by someone tuning this formula by hand. It's actually learned through machine learning. They show a bunch of web pages, they see which links people actually click on, then the next time those get ranked higher. And they have kind of some feedback loops, so they're always doing this somewhat automatically. And then they have to fool against different bots that search for a term and then click on whatever page they want to come up, and there's various games going on there too. So there's lots of other stuff, but let me try and give kind of the fundamentals, the basic ideas behind this. But yeah, but good question. So ask more questions. If you have. Okay, so so they basically do this. So there are going to be some problems with this though. Even the original PageRank algorithm that came out did not exactly use this. And before I talk about those issues, I want to talk about the computation a little bit. Okay, so there are essentially 3 ways to compute Q star. and there's kind of essentially one way used by that's commonly used. And we'll spend more time kind of going over essentially the more specifics about how they scale this up. But the first way is essentially what you're suggesting with the random walk, where you just send the crawlers out and you count how many times a crawler goes to a web page. You don't have to actually retrieve it. You can have the crawler actually walking around in your own internal copy and just you do these random walks and count this. This was like this, similar to this metropolis argument I talked about. The similar form of calculating it. So I said there were two ways of thinking about it. One was the random walk model. The other was you're actually building this vector. You can build it by doing random walks and count how many times you're there. But it turns out this is kind of inefficient and it's noisy. So this was inefficient and noisy. So this is not really how they do it. The second way, so then you want to think of maintaining this distribution somehow using this formula that's the limit as, any q0 times p to the n, and the limit as n goes to infinity is this q star, right? So one way is to set q star equals to q50, which is equal to p times p. So this was some vector p50. So there are 50 of these matrices times any q0. And in fact, you can use q from q star from yesterday. Remember I said that if you had a pretty good guess of what q star was, then you probably needed fewer iterations to get to it because you're already closer to it. So if I ran PageRank, the algorithm, last night, then I already had a pretty good guess. So I can plug this in as q0, and then I probably only need like 50 steps. So I don't know exactly how many steps they use now, but I've heard, 5 years ago I heard that they only ran at like 50 steps and they got a good estimate. They didn't need to run this, some 1,000 times or 1,000,000 times. They just needed 50 steps. Okay, so what's the problem with this approach of creating this big matrix? So to be clear, I'm creating this big matrix P50, and then I just take my Q star from yesterday and I multiply it by P50. What's the problem here?
Isn't it expensive? Since the matrix is big, isn't the computation expensive?
Yeah, it's expensive, but multiplying P by P itself is not too bad. But I mean, it's expensive, but not, the time is not so much the problem. It's that it's memory intensive. Okay, so most web pages link to only a handful of other web pages. That means that every column, even if there are 1 million or 1 billion web pages, they may only have maybe all zeros except for, say, at most 100 different pages. Maybe there are a few things like these indexes like Yahoo that have thousands of links, but they still don't link to every web page, right? So this is extremely sparse, this matrix P. And so already P7 may be completely full, may be completely dense. So there's this notion of the small world phenomenon that, so this is sort of the oracle of Bacon. Yeah, so actually a friend of mine from grad school maintained a website that actually allowed you to calculate the oracle of Bacon. So this is the idea that every actor who has a reference on IMDb, you can find 7 movies where that actor has been in a movie with, say, Tom Cruise, and then Tom Cruise has been in a movie with Nicole Kidman, who's been in a movie with Kevin Bacon. And this should never take more than 7 hops. So it's never take 7 more. And so there's this notion of small degree of separation, where for most people, you know someone who knows someone else who knows someone who is only seven people away from anyone in the world. There have been experiments where they tried to validate this, in fact, and usually 7 is not an unreasonable number. It's similar on web pages. You can get from most web pages to almost any other web page in only 7 hops. That means P7 says, if I were to jump 7 times, where am I likely to go? And so that means that this P7 matrix is already really dense, even though that matrix P is incredibly sparse. So that means that P50 is going to be really dense, and it's going to be really big to store, right? If I have 1,000,000 web pages and each has 100 links, then I need to store something like only 100 million links, right? But if I have a 1,000,000 by 1,000,000 dense matrix, this is like 1 trillion things I need to store, which is just way too big. My math is right. I think that's right, right? Okay. So this is too memory intensive, and that means it'll be too computational intensive, but the memory is really the problem. Okay, so then the third way of doing it is very similar here, but it's the idea that you, for I equals 1 to 50, set qi plus 1 equals p times qi. Right, so I just iteratively apply this matrix, but I only maintain the vector. And so this, because P is really sparse, each of these is essentially linear time in the size of the vector cube. So this algorithm is much more efficient, and you can do this at much larger scale. And so this is how they do it computationally, essentially. I'll talk about how they do it within MapReduce, which I'll talk about on Wednesday. So I'll talk about how they do this within MapReduce. It's a little trickier, and there are different variants of doing it. So I'll talk about that a week from today. Okay. So this is the computation kind of key. You want to not do it this way or do it this way. And I think the homework, you'll kind of experiment with some of these various ones. Okay. Okay, so now that we kind of know how to compute Q star, this PageRank vector, well, not really the PageRank vector, what is wrong about this? Why will this not work?
It's because still, if there is a page, it can change page rank of others by changing its content.
Yeah, but not too much, right? You really need to have, one edge is not going to affect things too much. So changing one page is not going to have too much effect. It kind of tells you about the whole structure of the graph. In order for this kind of whole theory to work here, we needed some properties, right? I spent all day Wednesday talking about all these technical definitions, and you're like, why is he talking about these things? And just tell me how this works, right? I said this only works if P is ergodic, right? Is P, the web graph, going to be ergodic? So what did it mean to be ergodic? So it meant not not cyclic, and as long as you have at least one page that links to itself, it's not going to be cyclic. So this is not really. So it has to be connected. Well, for the most part, there are some unconnected pages. Sometimes you'll post something you don't want to link to for various reasons, but for the most of the web is actually pretty well connected. The thing you have to worry about is transient and absorbing web pages. Right? So this was the idea that you have, this graph, over here that's, you know, that's happy, it's all connecting to itself. If you have one outgoing edge to here, and this page doesn't link anywhere, then all the random walks get stuck on this page. Right? So first of all, this structure does exist on the web. There are some large parts of the web that are linked to that don't link back to other parts of the web. I've heard something like 10% of the web is in some out chunk that you can't get back to the other 90%. Someone did some surveys some point years back. I don't know, it could be very different. So the other problem is spammers actually figured this out. They created something that's called a spider trap. Okay. Well, so actually I'll get back to this spider trap. We still need to fix this, and the fix will kind of defeat these spider traps, but not entirely. So how do we fix these transient absorbing pages? Okay, so if the way to think of this is if you're a random surfer, you're the person who's actually, you know, you have homework to do for my class, so you're off procrastinating, browsing the web, you know, going through Wikipedia, and you get to a page and it doesn't link to anything else, right? So what are you going to do?
Back button.
Backtrack. Yeah, you could backtrack. Yeah. So that's sometimes what you do. So that's not the right answer for fixing PageRank. No, that's good. So any other?
Start over.
So start over. So what does that mean?
Just go on Reddit instead.
So what you do is you're going to go to essentially a random web page. Okay, so you're going to somehow jump to a random web page. Now, it probably won't be random, and you probably have your pages that you like to jump to that probably link to a bunch of stuff, right? So maybe you go to CNN.com and it links to stories, and links to other stuff, or whatever the page of the day of Wikipedia is, something like that. But you're going to go to some other web page and then start surfing over it. And maybe you're only going to go 10 pages deep before you do this. So you're going to do this 10% of the time. Okay? So how does this change this graph? So it changes it in two important ways. One is it fixes these nodes, because you could get here, you have some chance of jumping out. In fact, if it doesn't link anywhere, then you always go to a random page. Even if you're at this page, which is inside of here, you may be kind of in a tight circle. So it could link, maybe this page links here, and this one links here, and then links back. So even though you can go someplace, you're never going to get out of this loop. So 10% of the time, you're going to jump to a random web page. And this means you go to about 10 pages deep, and then you jump off. And then you start over again. You probably don't go down the rabbit hole, that deep. Sometimes you go on one of these deep dives, but that's pretty rare to go more than 10 pages. And so it eliminates, that means from this page, I can go to any other page on the web. And that means it's no longer transient absorbing. I no longer have these sorts of states. So that part of this is good. But there's a bad part of this too, right? So if I were to store this in this matrix P, what's going to happen? Why was I able to compute this one so efficiently? Because it was sparse, right? Is it still going to be sparse? No, so it's no longer sparse. So this becomes dense, and now this computation becomes kind of trouble. Okay, so what I do instead is I'm going to use this update step, but instead I'm going to do qi plus 1 is going to be equal to 1 minus beta times p times qi plus beta times this vector, which is so there are m is equal to the number of pages. So and beta is going to be equal to 0.10%. Right, so what does this model say? It says 10% of the time I go to one page at random. I essentially pick a page at random. I don't have to actually store this vector. I can just pick a random number between 1 and m and go there if I choose it's 1 to 10% times. Otherwise, 90% of the time, 1 minus 10%, I do my surfing. I click on a link. And so I don't store anything sparse, anything dense here. This matrix is still sparse. This is, is only of size m, still the number of web pages, or I don't even actually need to explicitly store this. So this process is essentially just as efficient as this process. You can probably actually do it more efficiently because this part is probably faster, and then 10% of the time you do that. And it has this property that it doesn't have these transient absorbing states. So it fixes this problem. So by just 10% of the time going to a random page. So this has changed the structure of the web graph model I have. Right? It's not the same web graph model as if I actually followed the links. But that's probably okay. This was a model I made up, right? Think back to the part of class where I was stressing how we're building these models, and these are fairly arbitrary, so don't trust any answer too much. You can change your model a little bit and it's fine. I can change it by 10% and I'm still getting the same rough structure. I'm still getting roughly the same PageRank vector that I want on the importance, but I'm avoiding all these weird artifacts that I don't want. So this is basically, so the convergence of this process is the PageRank. So essentially Q50 is going to be the PageRank vector under this process here. And I've seen various numbers for beta between 5% and 15%. I think they use something like 10%. But who knows? They keep that under wraps, I believe. Okay, so this was really cool. This made that the whole web you could say how important a web page based on not just how many things linked into it, but how important the pages were that linked into it. If an important page linked to my page, and it was one of the few links on there, then it must be an important page, right? So if there's a really important page that I trust a lot and I think is important because a lot of other people point to it, and so if your web page is on the front of Slashdot or the front page of Hacker News, at that point a lot of traffic is going to go there because a lot of people go to Hacker News and they see that link. If it's on the front page, then you're going to get a lot of traffic, and that's essentially what this is saying. Hacker News is high rank because a lot of people go to it and point to it, and then if you're pointed by Hacker News, then you're going to have a high page rank at that point. So that's kind of how the idea of what the PageRank vector is doing. And so this means that you're really using the collective wisdom of the entire web to say the importance of these web pages. And this was a lot harder for spammers to beat. They couldn't just alter the content on their page or create these random dummy pages from nowhere that link to it to fool it. Though there was still something called a spider trap that can kind of trick Google, and there's still a battle between the variance of these spider traps versus PageRank to get the true importance of pages. So if you were a spammer, how would you create pages that looked like they had high PageRank, but really you controlled them? So you can create more than just your one page. You can create other pages. And you can do some other tricks on the web. What other ways do you see spam on other web pages?
Randomly post links to it.
Yeah, so these kind of these dummy links or these spam links, right? So where would you so you can create these links to web pages, right? So if you see so like a common place you see them is maybe on blog comments, right? So if you're reading a blog, you look in the comments section or any page that's allowing comments, you see these kind of fairly generic things people will post with a link to a web page. So most humans can actually decipher these and say, you know, this is not related to what the post was about, I'm not going to click on it. But they're not targeting you, they're targeting the crawlers. The crawler will go to that web page, it'll follow that link, and it'll point to a web page. And this will increase the page rank of that page. So they're posting these to try and fool the crawlers or to alter this web graph so that the page rank algorithm is fooled. Okay, so what would be the anatomy? How would I create something that has a high page rank? So I'm going to start with these many of these pages with the links in so I'm going to have these links in these blog comments. I'm going to have many of these web pages. I'll send out my bots and try and post as many of these links as I can. Where am I going to make them point? If I make them all point to a single web page, so if I want to, so if I make them all point to a fake page, this page is then going to have really high page rank. If you ever wind up on these pages, you're going to have a chance to point here. And so you're going to drive a lot of random surfing traffic here if this random surfer is dumb like a crawler. So this was kind of like this spider trap. This page would then have really high page rank. The problem with just doing this, though, is that this is also actually really easy this structure is very easy for Google to find. So they can find structure that looks like this. And they can identify it and say, this is really a fake web page. So actually how this works is you're actually going to point to a few of these other pages, these intermediate pages. And then you're not just going to have one fake web page. So you're going to have fake 1, fake 2, fake 3. You're going to have these fake ones. You're going to have a bunch of these intermediate nodes which you load up with PageRank. And then you're going to point to some subset of these pages. And so you're going to take all the PageRank and then distribute it to the pages you want. And so then you can have all these pages with PageRank built up on them, and you can sell this to people who want to buy this. And you can send it out to these pages you want to give high PageRank. And you can alternate these, and you can change the links here, because the blog comments, once you post them, it's hard to change. You can load up these pages with PageRank and then alter these links to kind of to the top seller, to feed the score this way. And if you kind of intermix the structure, as long as it's not too deep, you basically get 10 steps before you jump out of here. So if you're like 3 or 4 steps deep, you can hide different structure in here. And all the traffic is going this way, and it's all generating the high PageRank pages over here.
So couldn't you just treat links and comments as illegitimate?
Yeah, so you kind of try and do that. You try and weight down these pages, or maybe realize as blog comments and not use those as much. This is one way of creating these fake web pages, but you can create web pages with links in other ways as well. You can, if you get into someone's account here, they can create a web page, and you can they may never check, and you can have it linked to a bunch of stuff. So you can create a bunch of web pages on like Google Sites, right? Make your own web page with a bunch of links and point it to these. You can create a Facebook account, right? Facebook accounts point to what is interesting. You make a fake Facebook account and you point to a bunch of stuff, That's a way to do it. So log comments are easier to spoof than creating a fake Facebook page. But a fake Facebook page is kind of harder for Google to downweight and to find. So there's this trade-off, and the hackers, the spammers look into this trade-off and try and optimize the most bang for their buck. But they try all these things, and whichever, various ones are easier but are worth less. And so there's multiple ways to get these fake links starting to go. And maybe you want to link to your Facebook page that has all these links, just to make this the intermediate page, to trick Google a little bit. So there's kind of, then they have ways where they try and detect these sorts of things. So what Google will do is they will actually put something where you can put comments. They will try and do something where spammers will try and use pointers to it. This is called a honeypot. And then they follow those links and see where those goes, and they blackball those. So there's a whole ecosystem of techniques of trying to fight this. But modulo these things, this takes a lot more work than just changing the content of a page or setting up some dummy pages on their own. This is a lot harder to do. These require spoofing passwords, breaking the captchas, and so forth. And so it's a whole different thing. Okay, so that's one way of approaching it, is to kind of try and detect these. The other way, and I'll talk about a couple of variants of PageRank. There's something called, a different way of attacking this problem is called trust rank. Okay, and this is a simple modification of this way you do this PageRank update. Instead of doing this, you're going to update qi plus 1 is equal to 1 minus beta times p times qi plus beta times this vector t. So now t is t is going to be a trust vector. Okay, and so this is not going to be the full. This is not going to be the full list of all web pages in the graph. But this is only going to point to web pages which are somehow more trustworthy. So this may include like .mil or like .gov web pages. Somehow they're very protective over these web pages. Not entirely so anymore, but these used to be very hard to hack. So they would trust like a .military.gov or maybe even like a .edu web page. So if you have a web page at a university, this is worth more than like a site by MySpace or something, right? I think MySpace still exists in some form. So these are somehow worth more, or maybe like from Wikipedia, or maybe very high PageRank pages, right? So some pages, like the front page of Hacker News, it'd be harder to hack there, and if you did, still a lot of people would be going there anyways, right? So one of these web pages that has very high PageRank, you'll still jump to these. So you're only going to jump to these really trustworthy pages in this step here. You're not going to jump to a random page. And so what that's going to do is, if I have all these blog pages, or maybe some other dummy pages that I've set up, these are not going to get jumped to. These are not trustworthy, right? So not not blogs. Blogs are kind of the worst pages on as far as PageRank is concerned. Some pages, unless they have very high PageRank. So some blogs are really widely read, and so these would still be good, but most blogs are not going to get filtered out here. So a lot of this incoming links are going to be invalid. So then you can say, so I can compute, so if the PageRank vector is Q star, then I'm going to get this, so this is going to get T star, which is going to be the trust rank vector. And if for a web page, so if the, if Q star of a page I minus T star of I over Q star of I, if this is, if this value is close to 0 or very small, right, that means that the trust rank vector was much bigger than the PageRank vector. Then it's probably spam. So if this was small or negative, this is probably spam. So not only can I then say not link to this, but I can also identify if this was probably spam by other pages it links to as spam. And I can kind of modify the true page rank. So this trust rank may not hit some parts of the web as much, so you don't want to always trust this. You still may want to use this, the regular page rank vector, but then also have the trust rank and kind of verify that it's a real page. Okay, so this is another way that they try and get around spammers. Okay, so one more thing I'll quickly talk about is personalized PageRank. So if you've noticed now, a lot of times if you're logged into your account in Google, your search results will be different than someone else's search results. They kind of know the sort of things you like, and those things will pop up more. Right? So if I search for someone who's, say, a grad student at Utah, but they have a very common name, and so it will actually know that I'm probably looking for the person at Utah as opposed to some other person with the same name. So if you search for your own name in the web, right, on Google, most people probably search for their own page just to see what comes up. You probably think, oh, I'm on the first page of Google. Well, that's probably because they realize you're going to search for yourself and you want to find your own page. You're probably ranked higher than if you search from a random account or you're not logged in. So if you want to see how high you really rank on Google, you need to unlog from your account and then search for your name. So who has never searched for their name in Google? I'm impressed, but you've got a really common name, so it may not be. But you've never searched your name in Google. That's pretty amazing. You're probably the youngest person